Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is the cables, and more cables video. And as you take a look at the whiteboard here about the topics that we're going to cover in this particular video, I'm going to tell you right up front, maybe a little bit of a warning. This is a very detail-oriented video. And the truth is, when you're learning about these cables, what certification exams such as Network Plus really like asking are differences between some cables, some maximum cable lengths, that kind of thing. So to be blunt, there is some memorization in this section. I'm not going to dress it up for you, there is. And I don't like teaching by memorization. If you've ever taken another class of mine, I pride myself on teaching you not only what you need to know for a particular exam, but also what you need to succeed in the real world. So I'm not big on memorization, but when it comes to cable types, this is just something we need to know. And as with some of the other material in these videos, you may watch it and think, well, this is great, but after the exam, am I really going to need to know this? And the truth is, yeah, you will. And that goes along with cables, because as you learn different troubleshooting methods, where I always like to start troubleshooting is at the physical layer. And what is more physical than a cable? Nothing. So you've got to know these particular cable distances, you know, what the maximum segment lengths are, what their transmission capacities are, and that kind of thing. So again, if it gets a little dry here once in a while and we've got some lists of things that we need to memorize, just hang in there and take my word for it from someone who's been exactly where you are now, just taking in all this theory. You are going to find this helpful in the field. Because really, the first step in network troubleshooting is making sure that the network is physically sound. And this involves checking the network cards. This involves always making sure the power is on. And it involves checking the cables. You know, are the cables overextended? Are the correct cables in use for the job that you need done? There's one surprising cable in here that even if you're very familiar with this information, may actually surprise you. And the only way to be able to answer those basic troubleshooting questions is to know all about cabling. So let's put our heads down and let's get it done. The first cable type we're going to chat about here briefly is coaxial cable, much more commonly referred to as coax. Although much more commonly referred may not be the right phrase, because frankly, you don't see a lot of coax cable around anymore. But it's still out there in some legacy networks. And remember, in networking, we never say old, we always say legacy. Coax has a copper core that is surrounded by insulation. And the insulation itself, in turn, is surrounded by metal braiding. And the braiding is protected by the cable sheath. Now, the two major forms of coax you still see on occasion are thick net and thin net. Thick net is 10 base 5 Ethernet, and it's also commonly referred to as thick Ethernet. Thin net is 10 base 2 Ethernet, and again, it's commonly referred to as thin Ethernet. Now, you're going to see values like 10 base 5 and 10 base 2 quite commonly throughout this video. You're going to see them on your exam, I can practically guarantee that. And you're going to see them in the field as well. So let's get you up to speed on exactly what that means. Now, the initial number that you see there indicates the transmission speed of the cable in megabits per second. And so that means that any question that asks you about speeds on the exam, that should be a gimme for you, because there are no exceptions to that. You know, I'm always saying this is networking, so there has to be an exception. But there really isn't to that particular rule. So if you're looking for fast Ethernet cables, anything that begins with 100 runs at 100 meg per second, and that's fast Ethernet. If you're looking at 1,000 meg per second, anything that begins with 1,000 will match that. So that's what the first number indicates, is the transmission speed of the cable. Now here, we've got that word base, and what that means is baseband transmission. And again, you don't hear too much of that anymore because broadband has really taken over. So let's compare baseband and broadband for a moment here. Baseband transmission does not allow for FDM, which is frequency division multiplexing, and broadband does. And you're currently thinking, well, Chris, that's great, but what the heck does that mean? Well, frequency division multiplexing, basically that's what allows a cable's separate channels to carry data independent of what the other channels are carrying. Now broadband does allow for FDM, which is when a broadband cable allows cable TV and internet access, say, to be achieved over the same cable. So that's what frequency division multiplexing is all about. And again, baseband does not allow for that, but broadband does. That's another reason you don't see a lot of coax around anymore. Now, finally, the last number you see there in 10 base 5 and 10 base 2, that indicates the maximum length of the physical segment in hundreds of meters. So 10 base 5, we're looking at 10 meg per second transmission speed. We're looking at the fact that it is baseband and not broadband. And the 5 indicates that it has a maximum cable length of 500 meters. Now we've got an exception. You're probably thinking, well, this is great. We haven't had any exceptions to the rule yet. Here's one for you that I don't know if Network Plus will ask about it, but there are other. This used to be a very popular exam question. I think it's pretty much gone. But watch this 10 base 2, because 10 base 2 does not have a maximum distance of 200 meters. It has a maximum distance of 185. So that's really all you need to know in today's networks about thicknet and thinnet. You might not even need to know this much to work in today's real-world networks, but it doesn't hurt. A cabling type that you will see a lot of in today's networks is twisted pair, either shielded or unshielded. And what happens is the set of wires inside the cabling are actually twisted around each other. And, a common question when you're getting started with this stuff is, well, why do they twist them? Why do that? Well, we have to keep in mind when it comes to cabling that outside forces can actually hamper network performance. And I don't mean any sinister outside forces. I mean just regular crosstalk, for example. Crosstalk is generally the result of one signal adversely affecting a second nearby signal. And the symbol for crosstalk is actually XT, so be aware of that, because that's usually the way you see it expressed in documentation. Now, twisting the cables, or twisting the wires inside the cable, actually helps to reduce the impact of crosstalk on the signal that the wires are carrying. And this benefit increases as the wires are twisted around each other more and more and more. It prevents another data signal or another kind of electronic signal from coming in and impeding the ability of these cables, of these wires that are now being twisted to carry the data to begin with. Now, not coincidentally, the more twists in your cable, the more expensive the cable. Not all twisted pair cable is built alike. So this sounds like we would want as many twists as possible and not worry about the cost, right? Because we got to get the data there. Well, even with cost not being a factor, and I know that's never land, right? Cost is always a factor. But let's just say that cost is out of the equation and we don't have to worry about it, and we'll just buy this cable that has as many twists per inch as humanly possible. Well, we might not even want that, because the more twists that we have, the longer the actual wires are. And that can lead to a problem with attenuation, which I mentioned in another video, but I wanted to find that for you again here. Attenuation is the gradual weakening of a signal as it travels. And whether that's a data signal or a radio signal or a television signal, the signal is very strong when it leaves its origin, but as it goes out farther and further, just like a radio station that you start losing when you drive your car out of town, the signal gets weaker and weaker and weaker until it becomes unusable. So, as with so many things in networking, it's a very delicate balance. We want to have as many twists as possible to protect our signals from crosstalk, but at the same time, we don't want to make the wires too long due to those twists. So that's an individual decision when it comes to how many twists you want in your cable. Now, twisted pair comes in two main forms: shielded twisted pair STP and unshielded twisted pair UTP. That why is one shielded and one is not? Well, STP has an extra shielding around the twisted pair of wires where UTP does not. And this is another trade-off we have to consider because, again, what's going to be the difference between STP and UTP? It's going to be cost, because UTP is going to be cheaper than STP, and maybe you're paying for protection you don't need. So it's another delicate balance. You will really see more UTP than STP in most networks today, in my experience. That may not be true in yours, but for the exam and for the real world, let's take a look at the different types or categories of UTP. Now, if you've heard anyone mention something about, Cat 3 cable or Cat 5 cable, I know when I got started, when I heard the word cat, I thought of, something that meows. And they're talking about a category, not a cat. So, but generally you're going to say, Cat 3, Cat 5 cable, that kind of thing. Now, not all of these categories are used in networking. But I don't like telling you about Cat 3 cable and then having you say, well, what about Cat 1 and Cat 2? What happened to those? So I'm going to fill you in on those as well. And any speeds that I mentioned throughout this course, they are the theoretical maximums. And I can tell you point blank that you will rarely, if ever, reach the theoretical maximum in a real-world network. It's just one of those things. It's not, theoretically we should be getting X, but real world we're getting Y. That's just the way networking is. Now, Cat 1 is not even used in data networks to begin with. It's strictly for telephone connections only. Cat 2 will transmit up to 4 meg per second, but for our purposes, that's pretty slow. And that's one of those things, when we got 4 meg, it's like, wow, what are we going to do with all that speed? And now it's like, oh, 4 meg, it's really slow. So you're not going to see that kind of cable around in today's networks either. Probably the lowest of these cats you'll see in today's networks is a Cat 3 UTP, which has a capacity of 16 meg per second, or just meg. Cat 4, you really don't see a lot of that anymore because it's primarily used for token ring networks. And token ring networks, as I've mentioned once or twice in the course, they're not dead, but you just don't see a lot of them anymore. Ethernet just is a lot more efficient. You can use Cat 4 with Ethernet networks as well, with a maximum transmission of 16 meg for token ring and 20 meg for Ethernet. Now, Cat 5 is the one you're going to see most often today, and it can carry data at speeds up to 100 meg per second. This is fast Ethernet cabling. And to take advantage of fast Ethernet speeds, you've got to use at least Cat 5. Let's keep that in mind. If you have a fast Ethernet port on a router, but you plug in a Cat 3 cable, you are not going to get fast Ethernet speed. Your port and your cable have to be able to carry the load. They're working together. Now, there's one little gotcha here. You notice I show a Cat 5 and then a Cat 5e. That E stands for enhanced. And if you take a 1,000 meg per second device, a gigabit Ethernet device, that's the one that runs at 1,000 meg per second. If you take a regular Cat 5 cable and plug it into a gig Ethernet port, you're not going to get gig Ethernet speed. You're only going to get fast Ethernet speed. You'll get speeds of only up to 100 meg per second. To reach the full capacity, or even to begin to reach the full capacity of a 1,000 meg device, a gig Ethernet device, you've got to use Cat 5e. Very important detail there. I've seen that more than once. It's like, well, we've got this, gig Ethernet port. We'll just take a Cat 5 cable and plug it in. Well, you can do it and it'll work, but you're not going to get gig Ethernet speed. You're going to get fast Ethernet speed. So finally here we've got Cat 6e, and that actually runs faster than 5e. It runs at multi-gig speed, so that's where that E for enhanced comes in. Again, I want to mention to you, I want to stress the speeds that you see here in the videos are maximum speeds. They are maximum theoretical speeds. Good to know for the exams, but as far as actually reaching them in real-world networks, you probably won't be able to hit those. Don't mean to be a pessimist. That's just the way it is. Now, we've also got some networks. We broke 10 base 2 and 10 base 5 down into smaller parts so we could understand what they mean. And we've also got some 10 base T and 100 base T networks that you need to know about because they've got some rules. And let's break those down though, first of all. Now, if we take 10 base T, again, what does that 10 stand for? It stands for the maximum transmission speed, 10 meg. Base indicates that this is broadband. So far, so good. But the last value was supposed to tell us how long the cable length was, what the maximum cable length was in hundreds of meters. Well, T is not telling us much. Well, what the T actually stands for in 10 base T and 100 base T is twisted pair. And there's a lot more to know about 10 base T and some of its oddly named relatives. So let's take a closer look at that. A 10 base T network is going to use the star topology where each host is connected to a central device, whether that be a hub or a switch. You recall our discussion earlier about the different topologies. And this helps you and I to troubleshoot the network as network admins in a way because it's easier to troubleshoot a star than a bus or a ring. But the fault tolerance is also much higher in a star than a ring or a bus, so there's already a lot to like about 10 base T. Because remember, our star topology, when there's a fault in the cable or a port, the only host that is affected is the one using that particular cable or connected to that particular port. Now, here are the rules for a 10 base T network. And I put 543-100 in the paren. That seems to be a good way to remember these rules. This is generally just referred to as the 543 rule, though, so don't be confused. It's not like going to be an exam topic, but I just think it's easier for you to remember all this as 543-100. There can be no more than 5 network segments. There can be no more than 4 connecting hubs or switches, and there can't be any more than 3 segments containing hosts. Now, thanks to those rules, designing a practical 10 base T network can be very challenging. You don't see a lot of these anymore either, but they are out there and you need to be able to recognize them. And on an exam, I think that's good ground for a question to be able to look at a network and say, okay, does this meet the 543 rule? Well, you just can't have more than 5 network segments, you can't have more than 4 hubs or switches, and you can't have more than 3 segments actually containing hosts. The 100 comes in because the maximum segment length is 100 meters. Now I'm going to speak off the record here for a moment, or as off the record as you can when you're speaking into a microphone and being recorded, and to tell you that in the real world with the 10 base T network, you can have a segment length up to 150 meters. But the official rule is it's 100 meters. The official word is 100 meters. You'll see that in all vendor documentation. They always tell you 100 meters. And then finally someone pipes up and says, hey, you can't have 150. But really, you just don't see that much of the 10 base T network, so it doesn't get to be too big of an argument. Now, 10 base T networks are fine, but one major reason you don't see them around much anymore is because, frankly, today's networks demand more speed. We've got to have a lot faster network, and that's why we've got 100 base T networks. And here comes some of those things you're just going to have to memorize. The IEEE 802.3U standard defines fast Ethernet, and this is a 100 base T network. Fast Ethernet allows data transfer rates up to 100 meg per second while using much of the same network infrastructure that makes up a 10 base T network. So that's really good in and of itself. But we've got a couple of rules we got to keep in mind with 100 base T. Now that official limitation of 100 meters on a segment length is still in place. But as you can see, now we're down to no more than 3 network segments and no more than 2 connecting devices. So again, I would keep those rules in mind. There are your 10 base T rules. Again, that's your 543, the 100 rule. If you just want to call it 543, that's fine with me. But again, 100 base T, that's fast Ethernet, IEEE 802.3U, that's the official standard that defines it. You want to look that up on the net, and start looking at IEEE standards and documentation. I'm not going to tell you it's the most exciting reading in the world, but you can pick up some good information from them. And as I note, the most common standard for 100 base T today is 100 base TX. Now 100 base TX uses the same wire pairs as 10 base T does, which allows a host using 100 base TX to send and transmit simultaneously. That's what we really like about fast Ethernet, because we're not just, up to 10 times faster, comparing Ethernet speed of 10 meg to fast Ethernet of 100 meg. But the key is, with fast Ethernet, we can send and receive at the same time. A fast Ethernet port can send and receive at the same time, where a regular Ethernet port just can't do that. Now, as I mentioned earlier, some of the things we go over in this video, you certainly have to know the theory for the exam. It's good stuff to know, but you're just not always going to reach these numbers. And theoretically, fast Ethernet would allow a host to send at 100 meg per second and then receive at 100 meg per second at the same time for a total throughput of 200 meg. So that is our theoretical total throughput for fast Ethernet. It's actually 200 meg. But again, in the real world, this throughput level is highly unlikely. I mentioned earlier in the video when we talked about the Cat2 cable for just a moment having the whopping speed of 4 meg per second. And, at the time, it's just like, wow, what are we going to do with all that speed? And we felt the same way when we moved up to fast Ethernet from Ethernet. And when you first used fast Ethernet, and here was this port that not only could run 10 times faster than a regular Ethernet port, but also could send and receive at the same time, it just blew you away. You just thought, this is the pinnacle. This is as good as it's ever going to get. Well, we also used to think that a floppy disk had all the storage space we were ever going to need too, and you don't see too many of those around anymore. We've now moved up to gigabit Ethernet, and not to badmouth regular Ethernet or fast Ethernet, because gig Ethernet is certainly getting more prevalent every day, but it's not something you see on every PC or anything like that, certainly yet. Gig Ethernet runs at 1 gig per second or 1,000 meg per second, which is why I put both of those values at the top. And you should be ready to see either one of those either in documentation or on an exam, but they're both the same measurement. The first gigabit Ethernet standard was IEEE 802.3z, but the most common gig standard in today's networks is 802.3ab or 1000 base T. I told you there was going to be a lot of memorization of this one. I was not lying. 802.3ab requires Cat5e or higher. That's the one where if you put a Cat5 cable in, you're going to get transmission, but you can't reach gig speeds. You've got to have a 5e cable to get that to work or higher. Now, a key benefit to 802.3ab is the ability to use copper cabling that's already in place, because this will run over copper wiring. Now, there are a couple of warnings here I want to give you at the bottom regarding a couple of other gig Ethernet standards. 1000 base TX, again, requires category 6, and actually we'll go ahead and put 6E there. That requires a minimum of 6E. 1000 base T does not. It will actually work with the Cat5e cable. 1000 base CX, you really don't see much of this anymore either, and I think you can already see on the whiteboard why you don't see a lot of it. It's got a maximum segment length of 25 meters. And you may wonder, well, why did we ever develop anything in today's networks that has a maximum segment length of 25 meters? We're going to revisit our friend 1000 base CX here a couple of times during the rest of the video, so you'll see where it falls into the scheme of things, the greater scheme of things. But I would pay special attention to 1000 base CX. It's got a couple of real differences between anything else we're going to talk about. And the first one, of course, is the maximum segment length of 25 meters. Fiber optic cable. This is really the next great leap forward in cable types. And the reason is that the data is actually transmitted as light. And in turn, this means the signal is immune to EMI, electromagnetic interference. So, hey, that sounds great, right? I mean, the data is going to be light, and we don't have to worry about some things that we have to worry about the physical layer. We don't have to worry about EMI. So why don't we just go out and buy a ton of fiber optic cable? Well, it's still really expensive. It's not as bad as it was, but it's still really expensive. And not only is the cable expensive, but the network equipment required to use it is expensive, and to have it installed is expensive, and to have it fixed is expensive. Well, I just used the word expensive 4 times in one paragraph, so you can see why it's going to be a while before fiber is really commonplace. But you are seeing a little bit more of it and a little bit more of it as time goes on. How commonplace it's going to end up being, we'll just have to wait and see. Everything comes down in price eventually, but fiber has been a little slow to do so. Fiber cables come in 2 major categories, SMF and MMF, single mode fiber and multi-mode fiber. The single mode fiber uses a very narrow pathway through the cable itself to transmit that light signal. Now, this has a good point and a bad point. Now, this prevents the signal from diffusing or becoming weaker during the transmission, but SMF is really, really expensive. So MMF, which is more affordable, uses a core pathway that is 5 to 6 times larger than SMF. And not only this does allow for more diffusion of the light, but it also allows different light pulses to use the core paths simultaneously. So it's kind of like broadband versus baseband in that we can either carry one signal with SMF or multiple signals, pardon me, multiple signals with MMF. Now, I'm not comparing SMF and MMF to baseband and broadband in other ways, just that one way where SMF is going to carry a single signal and MMF is going to carry multiple signals. The other major difference between the two is that MMF is typically used for shorter distances when compared to SMF. For example, one fiber optic cable type we're going to look at here shortly, 1000 base LX, it actually runs in both MMF and SMF, but its MMF version has a maximum transmission length of about 500 meters, maybe 550, depends on whose documentation you're reading. But the SMF version has a maximum distance of 5,000 meters. That's a pretty big difference. SMF signal carrying 10 times farther than the MMF. So again, those are the big differences. It's really cost, the number of signals they're carrying, and the fact that MMF is generally used for shorter distances. And as I've got here, as I mentioned, here's the 1000 base LX that runs in both MMF and SMF, and you can see the SMF signal. The maximum cable length is much, much longer. I've got some summaries here of the different kinds of cable types. Some we've talked about to this point, some we have not. And I really want to put them in one place here for you so you can compare them, learn the transmission speeds we've talked about, learn the segment lengths, maximum segment lengths, the kind of things that certification exams enjoy asking about. And I say that only because I know it's easy to gloss over this material. It's not the world's most exciting, but it is material you need to know to pass the exam and really to be an effective troubleshooter in today's networks. So revisiting our friends 10 base 2 and 10 base 5, both of them just about obsolete. I don't want to say they're totally gone, but they're real close. 10 base 2 is also referred to as thin net or thin Ethernet. It has a 10 meg maximum transmission speed. It has a maximum segment length of 185 meters. 10 base 5, again, just about obsolete. We're talking there about thick net or also thick Ethernet, runs at 10 meg, and the maximum segment length there is 500 meters. 10 base T, 10 meg max speed. Like I said, anything they ask you referring to a speed, you can look right at the beginning number and be able to tell what it is. 100 meters maximum segment length for 10 base T, and it requires a minimum of Cat5 cable. Now here are a couple of fiber optic cables, and I want to point out this first one to you, 10 base FL. It's really easy to make the assumption that anything that, and I say just runs at 10 meg or 100 meg is copper cabling, and that all fiber optic cable is really high-speed cable. That is not true, because this 10 base FL cable obviously has a maximum speed of 10 meg per second. It does have a 2,000 meter, 2 km maximum segment length, but this is a fiber optic cable. There is such a thing as a fiber optic cable that runs at 10 meg, and this is it, 10 base FL. 100 base FX runs at 100 meg. It has a 2,000 meter or 2 kilometer maximum segment length, and it is an MMF fiber optic cable. So there are a couple of fiber optic cable types that we had not discussed to this point. Another fast Ethernet type here, 100 base TX. Again, it's 100 meg max speed, 100 meter maximum segment length, and it's going to require a minimum of Cat5 cable. 1000 base TX has 1000 meg max speed, 100 meter maximum segment length. It requires Cat5 at the minimum, but that's for fast Ethernet levels. If you want to get the full benefit of 1000 base TX to run gig Ethernet, you've got to use Cat5e at the very least. If you use Cat5, you're only going to get fast Ethernet levels. 1000 base CX, here's that little oddball we talked about earlier, and I'm going to mention it here again because I have 2 notes out of 3 lines, so there's got to be something funny about this one, right? This is a 1000 meg maximum speed cabling. The maximum segment length is 25 meters. Notice that this is copper cabling. This is not fiber optic. So, at the time we were all excited to get it. It's like, hey, copper cabling that runs gig Ethernet. But of course the gotcha was 25 meters maximum segment length. We'll talk a bit more about this connector type here, but this HSS-DC, the 1000 base CX cable is the only one I've seen that uses this particular connector. Again, 1000 base CX has a 25 meter maximum segment length. That's one drawback. It does use copper cabling. It is not a fiber cable, but it's also got a 9-pin connector, a high-speed serial connector. 1000 base SX, again 1000 meg maximum speed. I say up to 550 meters maximum segment length. If they happen to ask you about this cabling type on your exam, there's documentation out there that says it runs 500 meters maximum length or 550, and no one seems to agree on it, so I would go with the range of 500 to 550, and that should be more than enough. Designed for shorter distances, as I mentioned, and it is MMF fiber optic cable. 1000 base LX, again 1000 meg maximum speed, it's a gig Ethernet speed. Comes in both SMF and MFF, and the SMF maximum distance is 5,000 meters, where the MMF is only 550 meters, and again, that's one of those where documentation disagrees here and there, whether it's 500 meters or 550 meters, but anything in that range would be the limitation for a segment length for 1000 base LX running MMF. Just a few more, we're almost there. These are the 10 gig cable types that you need to know about, and that is 10 gigabits per second. That is some throughput. I also expressed it there as 10,000 Mbps. You could see it expressed that way, as well as the more popular 10 GB expression. Same thing, same speed. The big differences here are the maximum segment lengths and the type of fiber optic that they are. 10G base LR has a maximum segment length of 10,000 meters and is SMF. 10G base ER has a maximum segment length of 40,000 meters and is SMF. 10G base SR is MMF, but it has a maximum segment length of only 350 meters. I'm going to say that last one again. 10G base SR does have a 10 gig maximum speed. It's got a maximum segment length of only 350 meters, and it is a multi-mode fiber cable. Some fiber optic wavelengths you should probably know for your exam, because this is a part of fiber optic cabling, and what a nanometer or a nanometer is, whichever pronunciation you want to go with. This is the measurements used to measure the wavelength of the optical cable. And it would be a good idea for you to know these, since we're worried about, the maximum signal lengths and all the other values. So I'm not going to read each one of these to you. I mean, feel free to pause the video if you want to make some notes here. Do note that 1000 base SX and 10G base SR are the same 850 nm. And again, feel free to pause the video and jot these down if you like. Hey, here's the good news. We're past all that cable stuff, all the maximum segment lengths, a little applause, however you want to do it. Again, I'm definitely not saying that's unimportant material, but I know it's not the most exciting in the world either. But nice job. I do recommend strongly that you watch this video a couple times, take some notes, and pay particular attention to all those distances and maximum segment lengths that we were looking at there. In all this discussion about cables, we better keep in mind that without the connectors at the end of the cables, we really don't have a network at all. Because technically, when we connect, let's just say, a cable to the modem of a PC, we're not really connecting the cable to it. Technically, we're connecting the connector that is terminating the cable, because that's what actually physically connects to the device. Now, you've probably used an RJ45 connector without even knowing it. The RJ45 connector snaps into place. It's a UTP copper cable connector, and it's got a small plastic tab. When you snap it into the port or push it into the port, you should hear a little click as this plastic tab snaps into place. That prevents the connector and therefore the cable from just coming right back out if someone yanks on it a little bit. It's a very common connector. 10 base T, 100 base T, 1000 base T, they all are going to use RJ45 connectors. It's the most common connector in today's networks. The RJ45 terminates the 4 pairs of copper wires, and if you examine the connector, if you actually hold it up, then you can see the different color wires that are terminated in the 8 pins. And if you don't know what kind of cable you've got, either a straight through, a crossover, or a rollover, then you can always hold it up, hold end to end, compare them, and see. We'll talk about that again in just a few minutes. But let's talk about these less common connector types. The RJ11 is another copper cable connector, but it has only 4 pins, and it's used for standard phone connections. So it's good to know what that is, but it's not something that we would use in a network. An F-type connector, I really don't see many of these anymore, but they're generally used with cable modems. Here's that oddball that we were talking about earlier, and again we go back to 1000 base CX, which is like this. It's an exemption from everything. It's high speed, but it's not fiber optic. It's copper, and it's got that small distance. Remember, 25 meters maximum segment. Well, it also has an odd connector. The high-speed serial data connector, the HSSDC, is a 9-pin connector. It's quite the little monstrosity, but it is not a fiber optic connector. Please keep that in mind. It's not a fiber optic connector because this is not a fiber optic cable. Let's talk about some of these fiber connectors, though. And the one that's really becoming in vogue, but it's got a ways to go, is the MTRJ, the Mechanical Transfer Register Jack. And if you've worked with fiber optic before, you'll understand what I'm about to say. The hardest part of working with fiber sometimes is getting the connectors to work, because you're dealing with a whole new world when you're in fiber optic. And getting the connectors to work and stay connected and continue to work the way they should, that can be a huge challenge. Well, MTRJs are small form factor connectors that are easy to work with, and they're also easy to install. And having worked with them only once, I can tell you just from that one experience that it is a real improvement over the other connectors that we're about to talk about. This is also the only connector that has 2 separate strands of fiber, and they are contained in a ferrule or a ferrule. I personally don't care how you pronounce it, as long as you can read it. It is contained in a ferrule, and those are the 2 separate strands of fiber. This isn't prevalent yet, but it's getting there. As far as I see, it's the #1 connector for newer fiber networks, and I hope it stays that way. Let's talk about some of the other connectors, though. Another small form connector is an LC, and again, depending on whose documentation you look at, that either stands for lucent connector or local connector. The ST is a straight tip connector, but you don't see it often referred to just as ST because it actually uses a BNC connector. And the way you'll see it listed, if you do a Google search on some of these, which I urge you to do so you can see what the different ones look like, then the way a lot of vendors put it out there is ST-BNC. And it's unusual because BNC connectors are generally associated with ThinNet, and as I've mentioned, we really don't see much ThinNet anymore. So maybe they just had all those BNC connectors in a warehouse, I don't know. But if you do a search on that, you will see straight tip connectors listed as ST-BNC by most vendors. The SC, it's still out there. I do want to mention to you that's another fiber connector you can see stands for either subscriber connector or standard connector, and again, it depends on whose documentation you're reading. So it can't hurt to know them both. Believe it or not, we're actually going to move away from cable types and maximum distances and connectors and all that stuff, and we're going to talk about the terms used to describe roles that cables can play and some different kinds of cables out there in today's networks that you need to know about. And the first one is in a token ring network. Actually, you're probably familiar with a patch cable and how those are commonly found connecting a network PC to a wall outlet, which actually then leads to the patch panel, which then leads to the switch. Just depends on how your network is set up. But I want to alert you to the fact that patch cables are also used in token ring networks to actually interconnect token ring multi-access units. So again, we don't see that many MALs around anymore, but we do use patch cables to actually connect them. What's more common, though, is a situation where you're going to connect two similar networking devices. It's rare you're going to connect two routers directly via a crossover cable, but you could do it. Where you're most likely going to do it, though, is with switches. Because generally, you are going to have, and even just a middle-sized network, you're going to have switches that need to be able to communicate directly. And we cannot use a straight-through cable to do that. Now, earlier I was talking about how the wires go through a cable, and you could hold the RJ45 connector up and see the ends of it. Well, the cables we've talked about in this section have 8 wires, and when those wires run straight through the wire, that is, the wire connected to pin 1 at one end is connected to pin 1 at the remote end, and so forth for all 8 wires. That's a straight-through cable. But if we're going to connect two like network devices together, we can't use a straight-through cable. We're not going to cause any damage to the switches if we try to do that, but we're going to wait a long, long time before they can communicate. Actually, they'll never be able to communicate. What we have to use there is a crossover cable, and what actually crosses over is 4 of the 8 wires in the cable. So if you hold up the ends of a crossover cable to compare the RJ45 connectors, you'll see that half of the wires are in the same place and half of them aren't, because 4 of the 8 wires are going to cross over. Now, in a rollover cable, that's a highly specialized cable, and one use for it, a main use, is to connect a PC, generally a laptop, directly to a console port of a router or a switch. And you'll see these a lot during your CCNA studies, your Cisco studies. It's generally a blue cable, and it's going to look different than anything else you've seen. But what actually rolls over there is that all 8 wires roll over from one pin to another. Now, rollover cables, again, they were originally designed to connect to a 9-pin port on your laptop, but those aren't even on most new laptops. What we have, of course, are serial ports. So you've got to get an adapter for those. But that's a good piece of information to keep in mind, is that we use a rollover cable if we've got a laptop that we need to connect directly to, say, a router console port. I'm going to talk about a few cabling tools here, and not a great amount of detail with these, but you need to know where these would be used and how they'd be used. So let's talk about first punch-down tools. Punch-down tools are simply used to terminate cabling in a wiring closet. Now, that's the easy part. I don't know if you've been in too many wiring closets at this point. It just depends on, what your network role has been. Some are neat, some are not. And when you walk into some wiring closets, and even after a while, even if you're very organized, it's hard to keep a really neat wiring closet because you're going to have a lot of cables in there. Now, terminating cables, again, is not that hard, but tracing cables in a wiring closet can be a nightmare. And a couple of tools that we can use there is a tone generator and a tone locator. And those can perform cable traces in a wiring closet. Now, I don't know who came up with this name. I think this is great. The combination of a tone generator and a tone locator is known as fox and hound. And I first heard that working with a wiring closet guy, gosh, probably 8 or 9 years ago. He kept saying, well, we got to get a fox and hound in here. And I mean, I was laughing. I thought I was taking him seriously because the wiring closet was such a mess. But that's actually what a tone generator and a tone locator combination is fox and hound. So if you hear someone talking about that, that's what they're talking about. Do you really want to make your own cables? Let me give you a quick aside on this. I think it's good practice to get started with when you're really first starting with networking if you want to learn about the different kinds of cables. Generally, making your own cables is kind of false economy because cables are so cheap, and when you make your own cables, it's really easy to make an error. And the thing is, it's going to take you a lot of time to trace down the particular problem that you've got. But for those of you who want to make your own cables, hey, more power to you. Here are some tools you need to know about. The first tool you've got to have when you're making your own cables is the wire crimper itself. And what the crimper is going to do is use metal teeth and hopefully just a little bit of pressure to attach either an RJ45 or in some cases, when necessary, a B and C connector to the cable end. If you're using an older wire crimper, you may need a lot of pressure and you need to talk somebody into buying you a new one because older wire crimpers can be a real pain to work with. For those of you who make your own cables, you must test them. You must. Do not put them in a network and then try to figure out what's going on. A handy little tool called a wire mat tester can help you find shorts and transposed wires. And in my experience, those are the two biggest problems you have with cables that you make yourself. And again, I'm not really down talking it. I know a lot of schools that have networking programs have people make their own cables. The bad part is then they go try to put them in production networks without testing them. And you can test them very quickly with a wire mat tester. Now, a transposed wire, what I mean by that is it's connected to one pin number at one end and another pin number at the other end, and you didn't mean to do that. If you're making a crossover cable, you need to check some documentation online and see which ones need to be transposed. But if you're doing that with a straight through cable, obviously something's going to go wrong. So a wire mat tester can detect that very quickly. You could use one of these to determine if the cable is straight through or crossover too. But frankly, I would just hold up the RJ45 connectors and see, because sometimes crossover cables will be labeled, crossover, they'll have a little tape on them, a little tape label near the end when you buy them, but sometimes they don't, and of course those things fall off. So you might pick up a cable and say, well, is this a crossover? Is this a straight through? What is this? Again, you could use a wire mat tester just to make absolutely sure. But what I would do is just bend the cable and compare the ends in the RJ45 connectors. So two ways to do that. Always good to know two ways to do things for certification exams. Multimeters are also called multi-testers. And what these do, they measure the electrical voltage, current, and resistance going through a cable. Now this is an excellent tool to use when you suspect there's a break in the cable, because a multimeter is one way to test a cable's continuity and consistency. A better way, though, is with a time domain reflector. Sounds very Star Trek, but it's not. They're called, generally out in the field, you hear these called TDRs, and these come in all shapes and sizes. When I say that, I mean prices. You can buy a cheaper TDR, you can buy a more expensive one. But these also test a cable's continuity and do a better job, really, because we can test both metallic and optical fiber with a TDR. Another name for these are cable testers, but what you want to make sure you're doing is if you're buying one called a cable tester, make sure it's a TDR. Make sure the vendor is selling you what you're buying. Now, the big difference between the two is that a multimeter will let you know, yes, there's a problem with the cable. But a TDR can tell you where the break is. It's kind of like the difference between ping and traceroute. You know, traceroute lets you know that you have an IP connectivity issue, but traceroute lets you know roughly or almost exactly where the problem is. Well, a multimeter will definitely tell you, yes, there's a cable problem. But a TDR, how this actually works, it sends a pulse into the cable itself and waits to see if there's an echo. And if there is no echo, things are actually good, because what that means is that the signal hit the remote end of the cable and was terminated there. So there's no problem. But if you're using a TDR to begin with on a cable that's been used, then there probably is a problem. What the TDR will do is analyze the amount of time it took that pulse to bounce back. Because what's going to happen is the pulse will go down the wire, and when it hits the break, it's going to bounce back. And the length of time it takes for that to happen will give you, through the use of the TDR, an estimation of where the cable problem is. So it's really a fantastic device. I've used them several times, and they really can help you locate a cable problem. One more device I want to mention to you is a voltmeter or a voltometer. Even though there is no O in there, it's occasionally called a voltometer. These can help you detect the presence of a cable break, but that is not their primary use. I've seen this in documentation occasionally. What a voltmeter actually does is it measures the voltage between 2 points. Now, obviously, if there is no voltage between 2 points, you might just have a problem. I think that's safe for us to say. But again, as far as the devices whose primary purpose is to help us find that cable break, you really want to concentrate on the multimeter. As far as finding a break in the cable, they're relatively inexpensive. TDRs can test both metallic and optical fiber, and they will not only let you know that there is a problem, but roughly in the where the problem is in the cable. And that's about all we can ask for. That about wraps up our video here on cables, and the connectors and the testing devices and everything else. So thanks for hanging in there. Like I said, I know there's a fair amount of memorization in this section, but you'll find it worthwhile not only for the Network Plus exam, but for working with all these cables in real-world networks. So again, I would urge you, know your maximum cable lengths, know the NM values, the nanometer values, the cable testing. I hate to just say know everything in the video, but this is one video where you really want to watch the details and be prepared for questions on those details on exam day. So that about wraps it up for the cables. Go ahead and take a break, please, and I'll see you on the next video.